Now I'm very happy to introduce our keynote speaker for today, Joelle Pineau. And, you know, we mentioned this at the opening. We showed you a slide of the submissions to ICSE on the technical track. And this year we added the topic on AI and software engineering, and immediately it was the, I think, 6th most popular topic with 100 submissions marked as an area that, that their paper is related to. So I think we were thinking when we are putting together the program, we have to, being in the country that leads the machine learning research, it's appropriate to have a machine learning talk at ICSE, and we all know that you know, it relates to software engineering in many ways. And we were very lucky enough to get somebody who is a rising star or a star in the area. And I'm going to give some of the accomplishments of Joelle. She's an associate professor and William Dawson Scholar at McGill University, and she co-directs the Reasoning and Learning Lab there. And she also leads the Facebook AI Research Lab in Montreal, Canada. She has a Bachelor of Science degree from University of Waterloo, and she did her master's and PhD in robotics in Carnegie Mellon University. Her research focuses on developing new models and algorithms for planning and learning in complex, partially observable domains, and applying these algorithms to complex problems in robotics, healthcare, games, and conversational agents. Joelle has a lot of awards and recognitions. I'm going to list some of them. She's a fellow of the Association for the Advancement of Artificial Intelligence. She's a senior fellow of the Canadian Institute for Advanced Research. She's a member of the College of New Scholars, Artists, and Scientists by the Royal Society of Canada. And she's a recipient of the Stacy Memorial Fellowship. I hope I pronounced that right. And I think in acknowledgement for this award, it was mentioned that she's the driving force behind promising research whose aim is to use AI to improve the treatment of cancer and heart disease. And very recently, I think yesterday, she's received the Governor General's Innovation Award, and Joe told me that Governor is the Queen's representative in Canadian government, so, so these are the very impressive list of accomplishments. The topic of Joelle's talk today is building reproducible, reusable, and robust machine learning software. And I think this topic relates to us software engineers in 3 ways. One, I know that a lot of us are using machine learning in our research. So I think, you know, how reproducibility, reusability, and robustness of the techniques we use is important to us. I know that some of us are looking at using software engineering techniques for machine learning and robustness. For example, some people in the area, in our area, have worked on how can we help with improving robustness in machine learning systems. And another way this relates to us is that we in our community are very interested in reproducibility. And actually yesterday in the program committee discussion for the next year, there was a discussion on verifiability and reproducibility in our domain. So I think it's a very appropriate talk for us this year. So I would like you to join me welcoming Joelle to our ICSE.
Good morning. It's a pleasure to be here. Thank you very much for the invitation. As you'll find out through the talk, I'm quite passionate about machine learning in general, but more recently about issues of reproducibility and robustness. And so I have been on a little bit of a mission to share those ideas with people. I've done so extensively in the machine learning community, but it's really a privilege for me to come here and share some of these ideas with your community and hopefully learn from your community also about practices, issues, and how we might be able to work together to develop sound methodology and a sound scientific practice for our fields. I say this work actually stems in large part from some experimental findings in my group, but I think some of the lessons here apply much more broadly than this. In recent years, we've seen a large rise of interest in deep learning, very specifically in AI and machine learning more broadly. And in the course of that process, in particular with the rise of deep learning, there's been a significant move from machine learning as a very theoretical discipline to machine learning as a very empirical discipline. And as with any transformation, this has not always gone over very smoothly, and there's some challenges that have come out of that. And so in the last year or so, I've been sort of on a path to try to understand how machine learning as a discipline that is now largely empirical, an empirical science, how we should go about establishing the structures, the standards, best practices for our community. In particular, how do we enable researchers to produce high-quality scientific findings as well as high-quality software artifacts? And so my goal today is to share some of the findings I've come across on this path. A lot of the examples are going to be drawn from machine learning, reinforcement learning. I'll try to set the context as I go along. And then hopefully at the end we can have a discussion that goes a little bit more into the directions that might be of interest to you. And so it may not be directly clear to everyone why I picked those specific 3 R's. Why do I link them together? And so I found this quote in a report from the NSF 2015, not so long ago, that I think links them together in a better way than I could have. And so the quote is the following: reproducibility refers to the ability of a researcher to duplicate the results of a prior study using the same materials as were used by the original investigator. And perhaps most importantly, reproducibility is a minimum necessary condition for a finding to be believable and informative. And so this notion that we need to pay attention to reproducibility is not a new one. I'm definitely not the first person to call attention to this issue. In fact, 2016, the journal Nature ran an interesting survey. They queried 1,500 or so researchers across several different fields of science, asking them whether they thought there was a reproducibility crisis. And 52% of them said yes, they thought there was a significant finding, 38% thought there was a slight crisis, 3% said there's no crisis, and 7% didn't really know what's going on. There's a second part to this graph, which is if you cut up the numbers between different disciplines, things get interesting. Clearly the chemists are having a really hard time here. In dark red, we have the line of whether they had at some point experienced failure to reproduce results from another research group. And in pink, we have the results showing how many of them at some point had difficulty reproducing one of their own experiments. Not that far between the two. The biologists also having a bit of a hard time, on the order of nearly 80% of them failing to reproduce someone else's experiments, 60% of them failing to reproduce one of their own experiments. Computer science doesn't show up in this. I guess we're all folded under this other category down here. Still a reasonably important number. And so, you know, you might think that we're talking about a reproducibility crisis in this case. It's not necessarily a virus that's causing this crisis. It's not really because the chemists and biologists are affected that it's going to start infecting our communities also. But I would argue to some degree that poor methodology, poor scientific practices, once it gets incorporated in scientific reporting, can act as a little bit of a virus. Certain people put in place particular methodological practices that get replicated in other labs, and we end up with results, and I'll have examples from my own discipline, which leads us astray in our ability to have sound scientific findings. One of the reasons this is particularly timely is because we are at a period in time where more and more some of the AI technology which is developed in our labs is making its way relatively quickly into real-world settings which are affecting all of us. And so this progress doesn't happen overnight. You know, we're hearing about self-driving vehicles. Back in the days, when I was doing my own PhD, already we had some self-driving vehicles that could drive across on highways in the US. But certainly the level of sophistication of the technology is improving. And nowadays, at least in beautiful Californian weather, the cars are driving in crowded street and rush hour traffic with all sorts of dynamic elements around them. And so there's really a sense that though the technology isn't quite perfect, the changes are coming quite fast. And if we don't have a robust way to test the reliability of our systems, we may find ourselves in difficult situations. It's not just in transportation that we're seeing some of these major changes. Communication, social interactions are also quickly evolving. It's not so unusual these days to find yourself speaking to a bot. In some cases, you may be on a website interacting with a consumer service agent, not quite clear whether the agent on the other end is a bot or a human. Most likely, the early part of the conversation is a bot, and at some point in the conversation, unbeknownst to you, it gets transferred to a human if your issue is complicated enough. It's not just bots. In many ways, almost all of our interactions with the digital world right now are mediated by AI agents. What information you see, what information is communicated, how that information is ranked and presented is all controlled by AI algorithms. And so it's important that we understand what are the empirical properties of these algorithms and of these systems. Let me back up just a tiny bit in terms of the field of AI generally. I assume most of you are quite familiar with this. I want to draw the attention to the fact that as a research community, AI has actually, for most of its history, relatively short history, but first 50 years or so of its history, grown as a very fragmented community. And so in 1956, there was a seminal meeting at Dartmouth where the foundations of the field were really laid out and several of the sub-problems were identified. And from that point on, second half of the 20th century, researchers in sub-communities worked on computer vision, knowledge acquisition, natural language processing, decision-making. And what has really happened in the last decade, more specifically in the last 5 or 6 years, is really the sub-area, which we call machine learning, sort of taking over all of these other sub-problems and really being the driving force behind progress in AI. And so in the last few years, we've been able to achieve significant progress in all these other sub-areas through this engine called machine learning. It doesn't mean that machine learning will solve all problems, and I'll be happy offline to discuss about some of the problems I think machine learning cannot solve. But right now, this is the big force that is sort of powering through the world in terms of deployment and development of AI. And so if we look at this AI technology, there's sort of the two paradigms. The early paradigm was more a programmatic approach to AI, where the problem would be specified in a formal language that the machine can understand, given a very precise objective to solve, and search techniques, optimization techniques would be used to solve the problem. And this was very successful for very well-defined problems, such as building AI agents to play chess, optimizing airline routes, and so on. But clearly, there's a lot of problems in the world that we wish to solve where it's not possible to specify the objective quite so neatly in a way that the machine will understand. And so this is where machine learning takes over. And in that case, the practice is to show significant amount of examples, a lot of data, and the machine on its own learns to pull out the regularities in that data, usually by being given human annotations. And so this is the kind of technique that is used nowadays to segment and annotate brain tumors from scans from live patients. The machine learning pipelines, for those of you who haven't used the technology, works something like this. This is a little bit of a cartoon version, but I'll at least give you a flavor. Usually you start by getting some data. And often this is the point where some people who are not in the field start thinking we should be using the AI. We have all of this data, I have a disk full of data, so now I have a lot of clinical collaborators, for example, who start calling me up at that phase 1. I've got some data. Clearly, I must be able to do something with this data. Well, this is only the beginning of the road. Once you have the data, the next step is usually to clean up that data, to prepare it, in some cases to decide whether the raw data is really the one we should be presenting to the machine, or is there an opportunity to use human knowledge to take the raw data and transform it into an alternative representation that may be more digestible for a machine. Once we've cleaned up, prepare our data, we can actually train a model. And so a simple example in terms of cleaning and preparing the data is the work that's done on natural language processing. You have conversational normal text data. Often what we do is remove a lot of the very short words, all these kinds of articles. We simply cut them out. We take our verbs and we apply stemming. So we take the ending of the verb. Eat, eaten, eating, all of them gets mapped to the same word. And so as you can imagine, that really reduces the space of the language in a way that makes it a lot easier for the machine to learn. So once we've cleaned up our data, we pick some model. I'll describe some potential models, in particular neural networks you might want to use. You train that model. After you've trained your model, you test it on some data, and you see how well it does. And most of the time, we are in step 5, where we improve and try to see if we need to get more data, clean the data differently, get a better model, and so on. And this cycle repeats. Why is there so much interest in machine learning? Why all of this talk about it? I think this is one of the reasons why. The availability of data is growing very quickly. This is all human-generated data. This does not take into account all the data that is available in the natural world. If I think of like the DNA of all living organisms, that's not here. This is human-created data. The unit of measurement on the y-axis here are zettabytes. For those who don't remember, zettabyte is 1 with 21 zeros behind it. That's a large number, 1 billion terabytes, for those of you who are buying hardware for your lab. And so 2019, we're actually about 2/3 of the way in. Right around here, this is where we're at right now. 2025 is the end of this graph. We haven't extrapolated past that. For those of you who are teaching in universities, some of the undergrads in your classes will still be in school by 2025, and it will be their job to deal with that volume of data. And clearly, they don't want to sit down and sort through it visually and manually. They want the machines to be doing that. And so this is really the potential of machine learning, to extract knowledge out of this data and to extract value out of this data. There's incredible potential in terms of commercial values, which many industries have recognized, and that's why there's a massive investment in that area by several companies. But there's also an immense potential in terms of human and societal values. And so a lot of what we do is try to work with partners, in my case, particularly in the medical field, to try to achieve some of that potential. Once you have all of this data, there's actually an opportunity to learn very interesting, rich models of the data. And so learning functions of the data is essentially what machine learning is all about. And right now, the big flavor of functions that we are learning is the artificial neural network. And so let me spend a 2-minute for those of you who may not have had the primer on artificial neural networks, because it will come up again later on in the field, in the talk today. The analogy we make is with a biological neuron. So we have a biological neuron in your brain, very, very simple unit. You can think of that biological neuron as a unit of computation. Information comes in through the dendrites. There's a simple function that is extracted from that information, and then a message gets sent out through the axon through some of the other neurons. In an artificial neural network, you have artificial neurons. Each individual neuron very similarly takes in messages, in this case, several channels with a number, a real number going in. There's a small function that is computed inside the body of the neuron, and a message is sent out, which is the output. A single number is the output of that neuron. Clearly, the power of that representation, both in biological systems as well as in artificial systems, comes through stitching together vast amounts of these neurons. And so I've illustrated here a very simple artificial neural network. On the one side, we have the input layer. This is the raw data. If, for example, you're looking at predicting objects and images, the input would be the list of pixel values in that image. There are 2 layers of internal neurons. Each of the circle here represent one of these little function being computed. And on the output side is the answer. Is this a cat? Is this a dog that I see in this particular picture? When we talk about training the neural network, we are concerned with optimizing the weights of the connections between the neurons. And so I'm using theta to denote the weights. Sometimes I'll call them parameters. learning is all about finding the parameters that when computed together, the function will give you the output that you desire. And so you have to have a way to measure the errors that your system is making. We usually use a simple function. In this case, often squared error is the function that we use, though there's a few others in some cases. And we want, in this case, to find the set of weights that's going to minimize the number of errors. And this is done by a gradient descent algorithm. So step after step, we improve on our parameters in a way that we minimize that error function, and we look at the differentiation of our parameters with respect to that error function. When I said that complex functions get learned from large models, I really meant it. Some of the models for image recognition have on the order of 600,000 neurons, millions of parameters. And so as you can imagine, to train a system with that complexity, we need enormous amounts of data. Neural networks have had an interesting life. It's like the cat with 9 lives. They come in and out of fashion every decade or 15 years or so. And there's many reasons why this is so. One of the reasons is that if we go back to this optimization criteria, this gradient descent criteria, the complexity of optimizing that criteria is actually linear in the amount of data that you have. And so that means as the amount of data grows, the complexity of training the system still stays linear. If we compare to some of the methods that were very popular a decade ago, in particular support vector machines, decision trees, and so on, the complexity of training those isn't necessarily linear in the amount of data. And so it was completely fine to have an optimization algorithm that was quadratic complexity with respect to your amount of data when you had data sets with a few thousand examples. But when I have data sets that have 10 million examples, it's no longer feasible to do. And so in the case of neural networks, essentially, it can be linear in the amount of data, and so you can have very, very large data set and therefore train much more complex function. What can you do with this type of network has been evolving very quickly. I'm not going to give you a full survey of progress in the field. I'll give you just a quick taste. 2012 is where we really saw the rise of deep learning, in particular in a series of computer vision tasks where classical computer vision methods had been dominating. 2012 deep learning methods based on neural networks started to take over. Particularly the ImageNet competition was a big milestone. At that time, what computer vision algorithms could do is essentially look at an image, reasonably high resolution image, and in that image pick out 1 or 2 salient objects. So in this case, we get a global annotation from the image that says, in this case, there's some people and there's some trees. And at the time, we could do this with very high reliability compared to previous methods. And so there was a big jump, sort of 5% jump in terms of improvement, whereas the performance had been sort of stable or growing very slowly for the last few years. And we saw parallel improvements in other tasks like speech recognition, machine learning, natural language, and so on. So 2012, we can look at an image, pick out 1 or 2 salient objects. 2015, we start being able to put bounding boxes around these objects more precisely. 2017, we actually have very detailed segmentation maps of these objects with an annotation level for each object. So it's not just each pixel is labeled, but there's a notion that you can outline the objects. 2017, these kinds of techniques work mostly for objects that are for the foreground of the image. 2019, we are now at a stage where you can essentially annotate all the pixels in your image. You have a sense of depth between the objects that are much closer and the objects that are much further, and you have high accuracy in terms of the annotation of the specific areas of the image. And so all of this is essentially in the space of about 7 years. Now, if you start thinking what that means for several applications, we talked about self-driving cars. 2012, your self-driving car is taking a snapshot, and it's told there's a person. So you know there's a pedestrian somewhere. Is it to your left safely on the sidewalk? Is it right in front of the vehicle? You don't know. 2019, you have that information for all of the objects in the scene, including some notion of depth. You don't get very accurate depth straight from images. Usually the cars rely on complementary information in terms of depth sensors, LiDARs. But still, you have a sense of foreground and background, you have annotation, and you have precise object definition, not just some gross bounding boxes. And so huge amount of progress in a relatively short term. A lot of that progress is fueled by the availability of the data. Some of that progress is fueled by development of algorithms. And in recognition of this few months ago, the ACM announced that it was giving the Turing Award to 3 founding fathers in the field, specifically for their conceptual and engineering breakthroughs in deep neural networks. I would say there's sort of 3 main ingredients why we've seen this rise in deep learning. One of them is the data. One of them is the algorithms. The third one is the increase in computation. And so this graph gives you a sense of what has been the increase in terms of years on the x-axis for different key algorithms and results. And I will tell you right away that y-axis is actually already putting this on an exponential scale. So we have a logarithmic scale over here. And so the rise in computation has been a huge factor. Again, the graph starts in 2012 and takes us to 2019. Huge rise in terms of how much computing power we've been using to solve these algorithms. Fortunately, with all of this, there has also been a lot of development in terms of deep learning frameworks. So whereas when I started doing AI, you had to re-implement almost everything from scratch on your own, nowadays my students go in, they grab libraries, full frameworks, all of the systems that I showed you for computer vision are publicly available in open source format. It feels wonderful that you can go, as long as you have access to enough GPUs, just take this code, run it, and voila, you've got beautiful image recognition. And by the way, there's parallel progression in terms of speech recognition and recognition of several other modalities of data. So that feels very, very exciting. It should also be done with a little bit of caution, right? It's like you've got this magic wand all of a sudden, and if you don't know how to control the power of the magic wand, then you may not get the beautiful results that I showed you in terms of very accurate segmentation. And so there's a lot of sources of experimental variation that come into play when you use deep learning, and when you download one of these libraries and think you can just run it on your data as sort of a one-button push, I would say that right now we're really not there in terms of the state of the technology, and it takes quite a bit of understanding of the tools to get really the value that you hope out of them. And so some of the sources of experimental variation and some of the reasons why when you take, for example, the MaxCar CNN and try to run it on your data, you may not get exactly the same results, even if you're using the same library, eventually the same data set. The results may vary. In some cases, it's because of how the data was acquired. If you're applying this to a different data set, results, of course, can vary. How the data was processed, all of this cleanup procedure, what network architecture are you using? And by network architecture, I mean how many layers of neurons, how many neurons in each layer. And I didn't talk about this very much, but there's also a lot of work that goes into figuring out the connection patterns. We don't necessarily connect all neurons to all other neurons. And we have the same kind of architecture in the human brain. Depending on if you're looking at the visual cortex, the motor cortex, there are different connection patterns. We use similar insights in how we connect some of our neural networks. So how you do the network architecture can have a big influence. The activation function is the specific mathematical function that is applied in each neuron. And there's a few choices there too. So depending what mathematical function you put in each of your neurons, you'll get different properties. The weights that we're optimizing, I use theta to denote the weights. This is a gradient descent algorithm, so you need to initialize your weights before you start running gradient descent. It has been said by some of the best experts in neural networks that that particular factor, what's the magnitude in terms of your initial weights, is the most determining factor in terms of whether your results will be at the level that you hope for or not. It's certainly one of the important factors. The learning rate, so the step size when you run gradient descent, what kind of optimizer you're using, are you using second order methods and so on, can have a big influence. How you take the data, you use some of the data for training, some of the data for testing, how you split that data, and how when you're doing this on a distributed computing infrastructure, most of this requires several GPUs, what's actually the scheduler for doing that can also have a big influence. Let me spend just a minute on this notion of training and testing data, because this is one of the ways to control variation that we've had in the community for several years, inspired by researchers in the field of statistics who said, well, actually, if you show some data to your system, it can learn that data very, very well. And there's some early results in neural networks that show that neural networks are, in fact, universal function approximators. That essentially means that they can learn any function. If you just give them enough neurons and enough data, they will learn any function you want. That's probably not very useful in terms of transferring to new data you've never seen. And so common practice in the field is to always take a portion of your data for training this system, and then take a portion of your data that you put aside, and once you've trained your model, you're going to test the performance of your model on that data. You're going to report the number of errors strictly on that testing data. The holdout test set is essentially the best measure we have for a generalization error. That gives us a measure of how we would expect to do if we were to test it on other unseen data. And so a classic graph in machine learning looks like this one. On the blue line, we have the errors. You can think of this as just the number of images where we haven't labeled the right object. So the number of errors in blue on the training data. And we see that keeps on getting better and better and better with time, right? X is the training time of our system. So how many steps of gradient descent are we doing? And so over time, that keeps on getting better. That's great. We know it should go down to something very low because we have a universal function approximator and can learn everything. In red, we have the error on the testing data. And there's something really interesting that happens. On the testing data, it keeps on getting better until a particular period. But then after a while, the error on the testing data actually starts getting worse. And so this is the crucial point where our neural network goes from learning to memorizing the training data. And so usually we want to keep a close eye on that point and stop the model at this point over here when the test data starts getting worse. And that gives us one way to control the robustness of our system. Unfortunately, in many cases, that's not sufficient. And so it's a nice point to sort of pause and go back to this early notion of reproducibility, and particularly distinguish it from the very related notion of replicability. Right? And this is a definition I've taken from the American Stats Association. The study is reproducible if you can take the original data, the computer code, and reproduce all the numerical findings from the study. And it seems like that, as a minimum, should be easy. After all, computers, at least most CPUs, are very deterministic machines. You press the button twice, they should do the same thing twice. And yet that turns out to be remarkably difficult in many cases, some of which is for the factors of variation that I've listed not being properly controlled. Replicability, in contrast, is the act of repeating the entire study independent of the original, so going back to collecting the original data and so on. And in that case, we rarely do replicability. I focus mostly on reproducibility because we do expect to have a significant number of artifacts in most of the work that we do, including, in most cases, the data, usually the code. My own area, and the reason I got interested in this, is actually a sub-area of machine learning called reinforcement learning. And so for those of you who are not familiar with reinforcement learning, we are, again, interested in training an AI agent, but the difference is that the agent is not only making predictions, look at an image, tell me what's there, the agent is actually making decisions, and so it's carrying out physical actions in the system. They don't need to be physical, but it's carrying out interventions in a dynamic system, and we are interested in optimizing the sequence of these decisions. And so it's a quite powerful framework that can be used in robotics. We've used it to optimize sequences of treatments for chronic disease. In contrast to supervised learning, which makes prediction, this one really makes decisions and does so in a repeated way. So there's a dependency between all of the decisions that makes things a little bit more complicated in terms of the optimization problem. The framework is very general. The basic elements are the following. There's a state space, which is analogous to the input. The state describes all the information coming into the system. The agent needs to take an action. That action is applied into an environment, and out of that state and action, the agent gets to observe a reward. And that reward can be a very sparse signal. This is the kind of system we can use to play games like poker or the game of Go or backgammon. In that case, the reward only comes at the very end, the very last state. You know whether you won or lost the game. You don't get intermediate reward. Though in other cases, for example, in robotics, you can have intermediate rewards after every action. In the case of this framework, the agent learns by trial and error. And in fact, the whole foundation of reinforcement learning is inspired by early work in behavioral psychology, going back to Pavlov, who noticed that you could train agents, in his case animals, but it's also been applied in human psychology. You can train agent, in fact, shape the behavior of these agents by presenting a mix of rewards and consequences. And so those of you with pets at home, maybe young children, are probably familiar with this practice. The idea of reinforcement learning is codify this kind of intuition into a very specific mathematical framework whereby we train our AI agents with a similar mix of rewards and cost function, which the agent is designed to maximize. And so we've seen very impressive results of reinforcement learning in the last couple of years. Perhaps some of you followed the results in 2016 of the AlphaGo system, which demonstrated it could beat the best human players at the very challenging game of Go. And the success in this was the mix of using deep learning to represent the state of the board and reinforcement learning to optimize the sequence of gameplays throughout the agent's trajectory. We've also seen impressive results in 2017, 2018 from a system of deep reinforcement learning trained to play poker. The Librata system was developed by Thomas Sandholm, some of his students at CMU, and they were able to beat some of the best human players at poker also. And poker has the additional complication compared to Go that there's part of the state information that's not observable. Every player doesn't necessarily see the cards of the other players, so on top of that, you need to include some probabilistic inference in part of the state space representation. So pretty impressive results in terms of games. And as excited as I am about Go and poker, I am actually much more interested in all the other applications where we can use similar technology. And so there's actually been several works looking at applications of reinforcement learning. This is drawn from one of our smaller conferences, RLDM, Reasoning, Learning, Decision Making. The number of papers that treat different applications of reinforcement learning is really impressive. Crop management, I've seen some like fisheries management, forest fire, financial trading, controlling prosthetic arms, autonomous driving, energy trading also. So a large number of different potential in terms of application for deep reinforcement learning. You can probably see where I'm going from with this. You know, it's one thing to get it right in a game and maybe you win or you lose at poker and it's not someone's life that is in trouble. When you're looking at applying RL in some of these other applications, we're very concerned about getting it right and getting it right the first time. And so one of the projects that we've been conducting in my lab in terms of applications of reinforcement learning is in partnership with researchers at the Montreal Neurological Institute. We're trying to design strategies for neurostimulations for patients with epilepsy. So in this case, the state of the system is an EEG signal from the brain recorded in real time. The choice of action is the timing of the neurostimulation. The neurostimulation is an electrical current that is delivered as a small square pulse to the brain of the patient in real time, and has shown the ability to abort significantly the number of reduce the number of seizures that patients are experimenting. And so over the course of a few years, we've actually done this, in this case, in an animal model of epilepsy. So we had an in vitro model where we could induce seizures. We could read the signal, send it through a laptop, very much like this one, which decided on the timing of the stimulation, which was relayed via the stimulation electrode. And so in this case, clearly we want to make sure that works in the lab, in simulation with pre-recorded data, is going to work in the system. At this stage, we've only done experiments in vitro models for a variety of reasons, but one of which is I don't feel comfortable enough that the results are robust to carry it out to a more complex system. One of the big challenges is a lot of the successes of reinforcement learning we've seen are actually in games and in simulation environments. So I talked about poker, I talked about Go, but there's a ton of results showing you can use RL to play Atari games, fun stuff. There's a whole suite of 150 Atari games. It's wonderful if you're interested in doing sort of more academic research in that it's very replicable. I have my Atari games, I can share the code, someone else tests it, we can compare our algorithms, quite reliable. It also has the ability to generate millions of games, and I'm not at such a situation when I look at neurostimulation, doing recordings in an animal model. We have much smaller number of data. And so there's a lot that we have to learn in simulation that we then have to be able to transfer to our system. Most of the RL in the real world has to be learnable from a few hundred, maybe a few thousand trials. Whereas in simulation, and you'll see in some of the graphs coming up, we're looking at millions of simulations and action tries to learn the function. Most of the time when you're interested in doing an application of reinforcement learning that goes outside of the simulator, I gave you the whole list in terms of crop management, prosthetic arm, and so on. You look at the literature. You see what are some of the algorithms out there that are most promising that I should be using. And perhaps some of you who are looking at applying machine learning techniques in software engineering are doing the same. You scan the literature, you look at all the papers, you see which ones seem to have good results, and you try using those first. And so when I started working in reinforcement learning around 2000 or so, you know, the number of papers I had to consult before deciding which ones seemed most promising were relatively small, maybe on the order of 2,000 papers a year got published, and that was from much fewer in preceding years. Right now, you know, this graph does go up to 2018. The number of papers is exceeding 20,000 papers a year. There's been a huge rise in the field. In particular, you see the rise in 2017 after the results of AlphaGo in 2016. Big step function in terms of people interested in RL, producing papers in RL. But if you're someone who thinks RL might be a great tool for my particular software engineering application, then what you worry isn't just the 20,000 papers that were published last year. It's like this is the area under the curve that you have to worry about, right? Like all these papers from these previous years. And I assume you don't want to re-implement them all, and you would like to be able to read the paper and trust the results and assume that whatever results are in the paper will generalize to whatever application you want to do. This is the position we were in before I found myself thinking and talking about reproducibility. So let me share with you some of the things that we've learned by doing a systematic study comparing some of the methods in the literature. I will cast this in a specific type of neural network that is used in reinforcement learning. This is a class of neural networks that we call policy gradient methods. So assume that this blue box over here is a neural network, similar to the one I showed you before. The input to this is the state of the system, and the output is some distribution over the possible choices of actions. So a simple example that we'll be using throughout the experiment is the control of these simulated agents. So the state is the angular location of each of the joints in the little agent, and the action is some notion of power that we distribute to each of the joint to activate them. And so in this case, we want to set the motion of the agent in a way that the agent can actually walk and run in a relatively smooth fashion. And so we have input is the state, output is the probability of the action. The function we're optimizing is a little bit different than the one I showed you earlier. Earlier I had the mean squared error as a minimizing function. Here I'm trying to maximize the sum of expected reward. So you can think of the reward as being positive whenever my agent is standing, and the reward goes to 0 when my agent falls down. So we want the agent to be standing as long as possible, so we maximize the sum of reward over the trajectory. And we can apply gradient descent. In this case, it looks a little bit different than the gradient formula I gave you before because it takes account of both the distribution over states. Depending on what the agent does, you'll see a different distribution over states, so you have to factor that in to be able to maximize the expectation. So you have the state distribution, you have the derivative of the policy with respect to the parameters, so that's analogous to what we had before, And then we have the value function, which is essentially the estimate of this expected return. If you don't quite get all of the details in policy gradient, quite frankly, it doesn't matter all that much for the rest of the talk, but I at least wanted to give you a flavor of the type of network that we're using for reinforcement learning algorithms. So this class of algorithms is actually very, very popular. And so it's the kind of algorithm you might even want to use if you're doing like an optimization where you need to do like sequential setting of an optimizer in terms of using gradient methods. And just at the most recent NeurIPS conference last December, dozens of papers published using variants of these gradient descent algorithms. And so if I have a controlled task, for example, neurostimulation, perhaps control of a robot, I think gradient algorithms are the right ones for my application. I go to the literature, dozens of papers came out even just in the last few months. I don't have any ability to compare all these papers between each other. They all came out at the same time. The good thing is they're all using a relatively small set of baseline algorithms to compare themselves to. And so that small set of baseline algorithms, I've picked 4 of them that are the most used across the literature. They're relatively recent, 2015, 2016, 2017. There's been a big, as you saw, uprise of outputs. So most of these recent papers compare to these 4. So one of the things we tried to do is, look at what's the differential margin of each of the new approach with respect to these 4. And in doing so, we started asking, like, in some cases, different new papers were reporting different results for these baseline algorithms for the same problem. So that seemed a little bit odd. And so I'll give you an example. This is another domain. We call it the half cheetah. It's a half cheetah because it runs like a cheetah, but it's only like physically half of a cheetah, 2 legs. This is part of a simulation set called the Mojoko library, which is available if you're interested. I'll play it again if you missed my running cheetah. This is after training. The cheetah has been controlled. It can run. It has high reward. Things are beautiful. We looked at the baseline algorithms, 4 of them that are commonly used, and it doesn't matter for the purposes of today's talk which is better, which is not really. My message is sort of at a higher level than that, so I'll just call them algorithm 1, 2, 3, 4. And if you look at this one result, it seems like algorithm red clearly seems to be doing better than the other. Blue is totally out of the running. It's just not learning. X-axis is the number of training steps that I'm taking. Y-axis is my average return. So think of like, how long can my cheetah run? So on the basis of this, we might be tempted to think, red algorithm, clearly the best one. Let me use this to train my neurostimulation agent. It works well in simulation. I have similar characteristics. Let's see how it does. Fortunately, we went a little bit further, and we looked at 2 other analogous domains. There's a hopper environment where you're sort of a one-legged hopper agent, learns to hop around. And there's a swimmer environment where you have some kind of very simple swimming agent with similar physics engine underlying it as the half cheetah. So all of them are in the Mojoko suite. All of them are very similar. And I assure you the level of similarity between these 3 is much, much closer than between these and anything you might do in a real world. Once we ran these experiments, we were very puzzled. Hopper experiment shows that the blue algorithm and the yellow algorithm seems to be doing better. Red is actually at the bottom of this. Swimmer environment, sort of similar thing, but in this case, blue, which had very small variance in half cheetah and hopper, blue suddenly has huge variance, and the other 2 are less good, but much smaller variance. And so these were some early results that my students were bringing in, and full disclosure, we were actually trying to promote a competing method and to show that it was better than all these baselines, but the results on the baselines were so unstable, we sort of got completely, turned 90 degrees into a different kind of story, which is the one I'm sharing with you today. And so at that point in the work, weekly discussions with the students, clearly we're thinking like, oh, our implementation of the algorithms might not be good. And because there are all these libraries available on the web, the students hadn't necessarily redone all the implementation. They grabbed a library. So we decided, let's just grab a different library. Maybe this one isn't so stable, not so good. Student went back and said, okay, I found 3 different libraries for TRPO. All of them have a lot of stars on GitHub, so they must be good. Compare them all. All of them same TRPO, which is one of the 4 methods, and the results vary drastically. We thought maybe TRPO is particularly unstable. Let's try DDPG, which is another popular baseline, same kind of thing, like results just not really stable. Most of the time, we were running the algorithms in their default configuration. I'm not going to ask you to raise your hand if this is what you do when you download a machine learning package from the web. This is what we do. And here's the deal. When we started playing with some of the parameters inside of the code, in particular, some of these factors of variation that I listed earlier, we started seeing really different results. So here I'm showing you what happens if you use PPO, yet another of these 4 baseline algorithms, and you change the structure of the neural network. In blue, I have a neural network with 2 hidden layers of 64 units each. In red, I have 2 hidden layers of 300 and 400 units. And in yellow, I have 3 layers with 150, 25. Really different results. How do you know what's the right one? Well, if you have a simulator that gives you the benefit of endless data, you can test all the configuration, and the only limiting factor is going to be the amount of compute power. And at some point, Compute Canada or whatever is your provider of high-performance computing is going to cut you off, but until then, you can over-optimize to your configuration. We also see a very similar phenomenon when we look at the choice of activation units. So this is the little function that is going on inside each neuron. There's a lot of choices for those of you who might want to apply neural network. You might go with a tanh function. You might go with a ReLU function. There's the leaky ReLU, and this is just 3 of them. There's several more in the literature. Again, a significant factor. And if I dig deeper into other types of choices that you have to make, design choices, whether you are going to scale your reward function, whether you're going to do normalization of the output for each layer of your neural network, this sort of a popular trick that people are using in deep learning, all of them have a lot of factors of variation. And here's where there's a bit of a problem in terms of innate motivation of the researchers, which is all of what I've described applies to the baseline algorithms. We haven't even gotten to my new star algorithm, which I'm trying to promote. But the question on the table is, as a researcher, how motivated are you to find the best configuration for the baseline algorithms versus how much work are you going to put into finding the best choices for your own new star algorithms? It seems like that should be easy, right? Give everyone the same amount of data, same amount of computation, and we should be able to get a fair comparison. People don't always do this. There's definitely an incentive to do a lot more optimization on your own, but assume that you're doing this in good faith and you give the same amount of data, same amount of computation. You should be able to get a fair comparison. And so we did this. I sent the student back to the lab, and they had a very clear methodology of how to do fair comparison. They came back after a few days, said, Joelle, I've got this interesting result. You're going to really like this one. Here's the comparison we have. And so I look at this result, I'm like, great. Algorithm orange clearly doing much better than algorithm blue. Please tell me orange is your algorithm. We can write the paper and move on to something else. And I said, aha. Both of them are the same TRPO code. So both 2 baselines, both of them, they spend the same amount of budget optimizing the hyperparameter configuration, and they get significantly different results, 5 runs of each. And so we started asking, what is going on here? The only difference between those is essentially like 5 different random seeds going off in each of the 2, running on the same kind of computing infrastructure. And so this is a problem that we should have resolved. We know how we measure performance. We should have a notion of confidence that we can trust. And so, usually statistic tells us if you have a whole bunch of trials, you should report the mean of all these trials, average over a bunch of random seeds, and then look at the confidence interval, and we'll make some assumption that you have a Gaussian distribution. We maybe don't with just 5 seeds, but still, we're going to make that assumption. And the only question should be, how do we pick n? Like, how many trials should we do to get a reliable estimate of that performance? And we went in the literature, and I asked all these questions, and we had an interesting discussion. My students said, well, there's this funny thing going on in the literature, which I didn't know about, and they didn't know till they tried to replicate the results in the study, that the number of trials wasn't the same. And we looked at a bunch of papers. I don't want to reveal the identity of the authors of those papers because I don't necessarily condone this type of methodology. Most of them were doing 5 or fewer trials, and a few of them had started, and this is something that started creeping in around 2016, 2017, they started reporting just the top K results. So who knows what was the denominator here? They were running a whole bunch of experiments, but they would report the results of the top K experiments. And let me be very clear about what happens when you do that, right? Here I've run 10 experiments, I've reported them all, and this is the type of distribution that I get. And assuming I have a baseline to beat, if this is the result that I see, I don't have a paper, at least in terms of empirical results. If, however, I choose to report just the top 3 results, suddenly I have a clear winner and a story to tell. And so when you reduce the number of examples that you present, you have both a very strong positive bias, but you also appear to have a much smaller variance. And so if I'm looking at papers that are reporting results like this, and using those to decide which method to take to carry out in terms of a real-world application, I'm really not on sound footing. Some of these results have prompted people to come up with big titles on some blogs, like reinforcement learning never worked, deep only helped a bit, and it's got some foundational flaws, and so on and so forth. And this is not meant to be an indictment of reinforcement learning as a whole. This is meant to be a call for much more rigor in terms of empirical science. And it's also meant to be a call for those who are consuming and reading that literature to do so with a very critical eye specifically to the empirical methodology. And while the results I present here today are drawn from reinforcement learning, and so if I can pick on my own family, I assure you they exist in several other fields of experimental science across computer science. So what we have to keep in mind is that, we don't necessarily need fair comparison in terms of just giving same amount of data, same amount of computation. What we really are driving for is robust conclusion. That may mean that different methods have different sensitivities to hyperparameters. They may have a different set of hyperparameters. And what method works best might depend a lot on how much data and how much computation do you have. And if you're in a small data setting, small compute setting, there are methods that be much better than if you're in a large data, large compute setting. This in particular, in terms of deep learning, most of the results I showed you, the very impressive results on computer vision early on, were from data sets that were in the very large data, large compute setting. Whereas some of the work that is being done, particularly in terms of applications in the real world with humans in the loop and so on, are much smaller data, smaller setting. In many cases, neural networks are not the solution to those problems. So after having come out of all of these findings, we started talking about this results. We published the initial paper on this in 2017 and got a lot of interesting conversations going in the community from there. We went on and surveyed 50 papers from the RL literature, specifically 2018, so the year after we had published these early results. And we wanted to see sort of what's the state of the field in terms of producing reliable artifacts to enable reproducibility studies. So we picked 50 random papers. We checked all of them manually. All of them had experiments. This is great. That's kind of the initial set we want. 90% of those papers use neural networks, so that was quite interesting. Again, that's sort of the set that we want to be looking at. Most of them described all the hyperparameters they were using. Excuse me. Which is a good thing. So we knew what kind of learning rate they were using. We knew how many neurons and how many layers in their network. All the hyperparameters for the baselines were provided only 60% of the cases. So there was definitely a bias in terms of how much experimental details were specified for your own new star method versus the baseline methods. Code was provided. We didn't test the code, but there was a link, there was a URL there in 55% of the cases. The method for choosing the hyperparameter was specified in only 20% of cases. Evaluation on some variation of the holdout test set, so testing a little bit of robustness, was only done in 10% of cases, and significant testing was applied in 5% of cases. So there's some work to do. I particularly love these papers where they give you a graph and there's like a little bit of shade around each of the lines, and they don't define their notion of shading. Like, is it a confidence interval? Is it a standard error? Is it a 1 confidence interval, 2 confidence interval? I don't know. Shade looks good. We should apply shade. Okay, so I don't mean just to, sit there and point out the problems and criticize whether it's my own family or others. I think it's really important to engage in terms of finding solutions to this. And so I started looking at other fields. Like, clearly, we have a big job on the table for AI, but there's other fields that have figured this out at least to a higher degree in terms of reliability and robustness, 2 of them being aviation and surgery. These are cases where people's lives are on the line every day, and yet most of the time they manage not to crash and they manage to come out of the operation with a patient in much better condition. And one of the things they use is so simple: checklists. Checklists are fabulous. And so we went about creating the machine learning reproducibility checklist. It's available on my website if you want. The checklist asks that for all algorithms that are presented in a paper, one should include the description, the complexity, a link to the code. For any theoretical claims, we should have a statement of the result, a proof. These are the standard pieces. The interesting pieces beyond this are all the figures and tables that present empirical results should include a significant number of details, like a description of the collection process, the cleanup, how samples were allocated to training, to testing, hyperparameter considered, how you picked the ones you picked, some clearly defined error bars, a notion of what's the central tendency of the data, and what's the variation. You can pick whatever measure of variation you want. I don't care, just pick one and tell me which one it is so that I can interpret your results in a useful way. And the computing infrastructure use. I haven't spent a lot of time talking about infrastructure, but in fact, it can be a factor. Sort of earlier days of machine learning, it was a lot less of a factor. We were doing everything on CPU, single thread. Things were easy. More and more, we're moving towards distributed computation, large clusters of GPU, and it becomes a bigger factor. Some of the operations in CUDA are actually implemented asynchronously, and people are reporting some variation. So it's something to keep in mind, though I haven't spent a lot of time looking at that. And so there's another piece that's worth considering specifically for reinforcement learning, in that, I've spent some time telling you that in machine learning, it's important to have a training set and a test set, but then I showed you these results on these Majoko simulators that literally use like hundreds, if not millions of samples on the Majoko simulator, and we train on the Majoko simulator, and then we test on the same Majoko simulator. And so we're sort of in this end of the generalization roadmap where we're training and testing on the same task, and yet we're pretending that we're moving and making our way towards AGI, and there's a lot of newspaper articles that warn us about the fears of AGI, and we're sort of stuck in like training and testing on the same maze. So I think one of the things we also have to do, not only use our checklists and sound empirical practices, but also start thinking of how do we truly test for generalization? How do we get out of our data in a way that shows robustness, but without necessarily moving all the way to AGI? And so one of the things that we've really started implementing is to consistently have separate random seeds for training and for testing, and that separates some notion of variation between the training and the testing. This is something you can do in reinforcement learning quite conveniently. You can actually measure your performance on your training seed versus your performance on your test seed, look at the difference in the error. And when we do this on some task like the Majoko simulator I showed you, one of them is this Acrobat simulator, we see that if you use as few as 10 random seeds in training, your generalization error essentially goes to 0. And so that indicates to me, in this case where you have higher generalization error, you're the early part of the graph where you're learning. When you've got generalization error going down to 0, you're in the later part of the graph, going to memorization. You've essentially memorized your simulator. And so we shouldn't expect to get very good generalization. And I asked one of my colleagues at McGill, who does robotics work, this Acrobat simulator, if you do this on a real robot with 10 random scenes, can you learn the task? They can learn the task, yes, but it's really with many, many more random seeds than what we have in the simulator. So our simulators necessarily have very small amount of variability. Some of the simulators from Mojoko are written with a small number of lines of code, and as few as like 30 kilobytes, you essentially have captured all of the complexity of the simulator, no injection of natural noise. Meanwhile, the natural world has incredible complexity. A standard Bumblebee stereo vision camera, like the kind of stereo vision you'll have in a robot, can acquire on the order of 10 megabytes of data per second. The world we live in, it's been estimated that there are several zettabytes of human-made information. I showed you that. But the human body itself has, in terms of information content, on the order of 150 zettabytes. So huge amount of information in the real world. Meanwhile, we're training our reinforcement learning in simulators with a tiny bit of complexity. And so there's a big push in some of our work, but also work of other colleagues. This is work from colleagues at Facebook AI Research Lab, Facebook Reality Lab, and colleagues at Georgia Tech, really building simulation environments that have very high level of photorealism. They take these environments in terms of real pictures taken in real people's home. They stitch these pictures together in a way to form a 3D representation of the space. And now you can deploy RL agents that navigate through that space, interact with real images, so much higher complexity in terms of the world. And so we're moving away from simple simulators and games towards these kinds of much richer engines, and doing that in a way that's replicable. Because you could always do RL in robotics, and then you would deal with the complexity of the natural world, but it's harder from one research group to the other to compare results when we don't all have the same robots. In this case, with these simulators, we can do that. We can achieve much better standard of reproducibility, but do so in more complex environment. And so a lot of what we need to do is figure out how to bridge that gap from the works that done in simulation. There's perfectly good reasons to do some of your work in simulations, wonderful environment to do some of the early work, but then to connect that with the real world. Let me take just a few minutes to give you a taste of what's next in terms of AI and machine learning, and then I'll wrap up with a link back to some of the things happening on reproducibility, at least in our community. Maybe it will inspire you, maybe you will inspire us. In terms of machine learning specifically, I've talked about supervised learning, which is, like putting labels on images. I've talked quite a bit about reinforcement learning, which is where I spend most of my time. There's a lot of activities these days around generative models and generative learning. And I think in terms of future areas of growth, this is where we're going to see most of the interesting results. What I'm showing here are two examples of systems that have been built to create images. The images on the left, the two faces here, are purely synthetic. There's absolutely no one in the world that looks exactly like this. The quality of generation of images has progressed incredibly fast. These images are from late 2017, produced by a research team at NVIDIA. If you think they look particularly good for like random sample of people, it's because they're trained from a data set called celebs, which is all pictures of celebrities. So when you train with all pictures of celebrities, you get synthetic images that look something like this. We could spend a lot of time talking about biases in data set and how those biases induce something in how you make decisions. I'll leave that for the coffee break. Beyond creating images, there's been some really fun applications. At the top here, I have images from Van Gogh, original images from the painter. Bottom, a reimagination of these images by a tool called Deep Dreams, really recreating what this could mean. What's fantastic is, you can go from top of the left, if you think of some of the implications of the ability to generate high-quality images, high-quality sound. We have very good voice synthesis. I don't know if some of you followed the results. Google put out some voice synthesis in the last few months that is really high-quality ability to imitate a particular individual's voice. I would say the next frontier is the generation of video, and within about 2 years or so, we should have the ability to generate very realistic videos. A lot of concerns in the community about that rise of technology. At the same time, the same kind of technology for generating images is actually used for reconstruction of MRI images. And so we are developing a system. It's going to be in clinical trial in the next few months, that shows that instead of spending 50, 60 minutes in an MRI machine to do image acquisition, you could be there for 5 or 10 minutes and you will get an image with the same level of accuracy. You just have to take a subsampling of the images and use AI to recreate the rest. And so, you know, there's sort of both sides of several of this technology, and we have to think quite wisely about how we develop it and how we use it. Incredible progress in terms of generative models for natural language. This is from the GPT-2 model that was produced by OpenAI. In the last few months, again, the ability to start with a small language statement. In this case, in a shocking finding, scientists discover a herd of unicorns living in a remote, previously unexplored valley in the Andes. And then you ask the model to complete the story. It says the scientists named the population after their distinctive horn, Ovid's unicorn. These 4-horned silver-white unicorns were previously unknown to science. And it goes on and on. And so the length of text that you can have that is coherent from a grammatical perspective, but also from a semantic perspective, is impressive. These models are very large. OpenAI got into a bit of a controversy, basically saying they were not going to release the model because it could do more damage than good. I think there's a lot of ethical questions coming out around these generative models that will have to be taken into account. And the reason I spent a little bit of time talking about generative models with this community is because one of the applications of these generative models is for program synthesis. And so there's been a lot of progress on this also. This is from a 2016 paper by Alex Grave and some of his colleagues called differential neural computers. I will warn you that the type of programs that they are generating at this time is extremely primitive. Much more primitive than even assembly language, very small number of primitives in simple read-write operations. And so, you know, we're very far from the type of languages that are being used nowadays for programming. But I would just say, given the speed of the progress that we've seen in other areas, I would expect a large amount of work in this area. And as we move towards AGI, artificial general intelligence, there's really this notion that one of the frontiers is sort of computers writing their own programs and so on. And so it's something to keep an eye on and to see where it's going in terms of progress of that technology. Let me just conclude. I think if you just, I think, take one message from today, one I hope you take home, is the fact that, you know, science, and this is what I think many of us are doing, science should not be thought of as a competitive sport. It's not just about creating some interesting narratives. I know we all do that when we write our papers, but still we should remember to always embrace science as a collective activity where we communicate and we strive together to understand and explain the natural as well as the artificial world. In terms of what we are doing in the machine learning community, since I've started talking about this in my own community, I've been asked to take on the responsibility of being the reproducibility chair for NeurIPS, which is our largest conference. And so we've been thinking through a program of activities to support that. This builds on 2 editions we've run of the ICLEAR Reproducibility Challenge. So ICLEAR is a smaller conference, international conference on learning representation, which has an interesting property that it uses an open review system. So during the review period, all the papers are openly accessible for the reviewing committee, but also for anyone on the outside who can add comments to the papers. That has allowed us to run in parallel with this a call for participants. And so I've put out a call to people teaching machine learning classes around the world to ask their students as part of their final project for their graduate machine learning course to take a paper that is under submission, reproduce that paper, write a report of that, and then post it on the discussion board of the ICLEAR submission website. The reviewers and program committee were completely free to take it into account or not during their review process. It was an independent process that was simply facilitated by the fact that ICLEAR used reproducibility, ICLEAR used this open review platform. We've run 2 editions of that in both cases. On the order of about 100 papers were reproduced. We ran a survey of authors after. Most of them were very positive in terms of the quality of the feedback that they got through that. Essentially, people pointing out flaws in their methodology, sometimes just in the clarity of their writing that really helped improve the quality of the paper. We have selected a few of these reproducibility reports. We've ran a call to do a journal issue of just reproducibility results. And this was published just last week in the journal Rescience. We have a special issue, 4 reports that we've turned into journal papers. The report is there. The code for the reproducibility study is there. Sometimes code for the original paper was available, sometimes not. And so we will be looking at doing more of these special issues over time. And as part of our activities for NeurIPS 2019, I got a little bit carried away. I wrote 2020 here, but this is still 2019. NeurIPS is happening in December 2019, so we have to get all this done before end of the year. The machine learning reproducibility checklist that I presented, and I first presented when I gave a keynote at NeurIPS in December, now has been integrated into the submission process for NeurIPS. The deadline was last week. From what I understand, they got on the order of 8,000 papers. Every author was mandated to fill out this reproducibility checklist before submitting their paper, before it could go in. They had full flexibility about what information they provided in there. There's no correct or incorrect answer. Most of the time, it's really used as a self-reflecting tool to make sure that your paper contains all the information that it should. There's an encouragement to submit code with the final paper submission. It's not mandatory, but strongly recommended. And we will run a reproducibility challenge, again, where people take the papers that are submitted, try to reproduce them, write a reproducibility report. In this case, we're going to run it after the paper notification, so between October and December. Let me conclude here. I have the pleasure of being here with you this morning, but there is, of course, as you suspect, several students, collaborators that are behind a lot of this work. The RL reproducibility work was done mostly by Peter Henderson and Riyashat Islam. The work on reproducibility in the special issue for science was done in large part by Kustuf Sinha. And I'm forever inspired by all of my students at McGill, as well as my research team at FAIR. Thank you very much.
Thank you very much for an awesome talk, and I think we have plenty of questions.
Sure.
Lutz Brechelt from Berlin. Thank you very much. I worked in neural networks in the 1990s and did some work on reproducibility then, and I'm quite depressed to hear what you reported. When I think about the reasons why authors might fall so heavily short of reporting what's required in terms of parameters and methods, I can think of the explanation they were trying to cheat to get a publication, or the alternative one of a massive level of incompetence rather than just a small. Can you offer a third, less depressing explanation?
I would probably support your 2 explanations, but in a much milder fashion. And so I'll tell you the case, right? I showed you the results of what happens when you just report like the top 3 results, right? And so honestly, students in my group started doing this. And I didn't catch it for a while. They would just bring me the graphs and they'd have the little shaded area. And then there was weird things. We dug in and then we got out. They weren't purposely hiding it from me. It's just they were doing it because that's what the papers they were comparing to were doing it. And they wanted to have a fair comparison. And they're like, they're doing this, so we're doing this. And when I realized this, I was like, we can't do this. Like, we understand that this is not the right thing to do. And I don't really care if these papers are doing this. We're not going to do this. But it was not an intent to cheat. It was an intent to do a fair comparison. I don't know at what point someone decided to do this versus that. There's an incentive to say, maybe they were testing a very high variance method, and we make this Gaussian assumption over our error, but often it's bimodal with reinforcement learning and with neural net. Like, it converges or it doesn't converge. And so they said, well, we have the compute to run several trials, so we'll just take the results on those that converge and exclude the data, right? In other fields of science, there is that same issue that, you discard a lot of data under the hood, and now they're trying to fight some of that by getting people to record their studies in advance and so on. So I sort of agree with your 2 hypotheses. At the same time, I just think it's a much more mild version, but it's our job as members of the community to just uphold a higher standard, and that just has to be done every day. And it has to be done with some sympathy and compassion for the young researchers who are trying to make a career, but still trying to really impress on them the importance of good methodology.
Thank you.
Hi, Professor Pineau. I enjoyed your message about collaboration in science and kind of the importance of working with other communities. Thanks for the talk. It was really great. I have a kind of question about the reusability aspect of your presentation. Yesterday there was a talk here kind of questioning the impact of software engineering research on practitioners. And it seems like, well, this is one set of problems, but in machine learning community, maybe it doesn't have those problems, but slightly different ones in that you have kind of a lot of tools that are useful, but the kind of, it has a reputation of being kind of, you kind of have a lot of parameters and you have to do a lot of tuning. And the efficiency of kind of reproducibility so you have some existing techniques that work well. You went over a few from model-free algorithms and reinforcement learning, and there's kind of this parallel debate in the machine learning community about having these rich structured priors about the world. And I think of this kind of an analogy as engineering in some way. So we have a lot of literature in these little communities like robotics and software engineering that are that have a really kind of robust understanding of the world around us and the kind of rich details inside of that. So I guess the question in the comment is, yeah, how can, so with these kind of compositional inductive priors and the importance of kind of programming languages and the computer science curriculum that we have, how do you think we can kind of make machine learning more reusable, kind of composable, modular, and
yeah.
Thanks.
I think there's two aspects to consider. One of them, and that has been definitely a strong current in the field in terms of making it easier to use, is to have these frameworks and libraries be available, right? I mean, when I learned about neural networks, I was implementing backpropagation from scratch by myself, which I think is a wonderful thing for anyone studying machine learning to do once in their life. You don't want to do it too often. And so there's all these libraries and these frameworks that make it quite easy to just start and run it and to do it quite blindly. And so I think there's an opportunity to be more transparent about which of the knobs have a high factor of variation and which of the knobs are really stable. And by knobs, I mean these kinds of hyperparameters and design choices. And right now, we don't always have that. Like, you take the library from the web, you leave everything as default parameters, you press play, and you see what you get. And if that doesn't work, then you dig into the code, and it's not always in a very pretty state. So there's some work for people to do in terms of being much more transparent about what are the factors of variation, to have ablation studies where they take in, take out particular pieces, bells and whistles of their algorithm. The type of libraries that are available, there's always a higher level of abstraction at which people have access to control. So now in particular, with some of the optimizers like Atom and RMS Prop and so on, they try to do a lot of the optimization directly for you in an adaptive way. So we're trying to take away some of that responsibility, but then you lose some of that control. I would say as a complement to this is, in many cases, a lot of the influence is in the early steps, like what data do you choose? I gave you the example of the image generation that was based on celebrity data, right? We have huge issues in terms of biases of algorithms that creep in at the point of selecting what data is used for training. How is that data cleaned up? How is that data encoded? And so I think there's a responsibility on anyone who uses machine learning to spend time thinking about what is the data that they're using for training and what does that mean in terms of where you intend to deploy the system. And that's one place where our human knowledge is incredibly important.
Thank you very much.
Let's take a question, one from the back, right, on the right side, right there.
Hello? Hello?
Okay.
Okay.
Merci, Joelle, for this fantastic talk. As a software engineering community, our goal is to produce programs that produce outputs from inputs. And machine learning is a fantastic way to help us automate this tasks. The research done now is replacing the traditional programs by these black box models that produce outputs from the inputs. But we are facing the problem of explainability, testing, and all these kind of problems. The other direction, as you mentioned in one of your last slides, is to generate the programs themselves rather than learning the output. But you mentioned that this is at the early stages. So what are the obstacles? What are the difficulties of having this learning of complex structure, complex program, executable programs?
Yeah, I think it's an interesting question. I'll talk specifically about program generation, right? I think there's possibly 2 or 3 main obstacles. One of them is that programs inherently have a different structure than the other type of data that we've been generating. So I showed you the example of text generation, right? The text about the unicorns. All of our algorithms for text generation do so in a linear fashion. So they start with the first word, they give the second word, the third word, and so on. And I'm not an expert in software engineering. I'm guessing most people don't program in a linear fashion, right? Like you program a block, you add another block, you add another block, you change this block to fit with that block. And so there's a sort of global optimization problem that goes on, but then you're looking at something locally and it has to be coherent locally and it has to be coherent globally. And the type of models that we have for structured data neural network don't have the right priors for that type of generation. So we generate images. In images, there's a lot of local consistency, and then there's a few edges. And so we use a particular class of networks. There's, convnets and UNets and so on, specific architectures that are good for that. For text, it's all linear, and so we use recurrent neural networks, LSTM, that are good at that. I think for program generation, we just don't have the right priors on our architectures to be able to do that. And the people who've started doing it use mechanisms like attention and memory that are inspired from language, but I think they don't yet have the full flexibility that is required. Now there's starting to be graph induction methods where people generate relational graphs, think of like a knowledge graph, which may be a little bit more amenable, but someone's going to have to really dig into what's the right representation for doing. So I think that's one. The other big obstacle I see is the fact that programming is incredibly expressive. So the space of things you can describe with a program is very, very large. That means that the optimization problem you're solving is very high dimensional. And even though neural networks are, we know, universal function approximator, still, that means that you have to pick the one program in the space of all programs that is the right one. And that brings me to point number 3, which is with a computer program, you get 1 comma wrong and the whole thing is off. If I show you the image generation, I change 1 pixel, nobody's gonna notice. And if I talk about unicorn instead of unicorns and I get a little spelling mistake, nobody's gonna notice. In a computer program which you intend to run, there's a lot of very small things you can get wrong that are completely going to break your computer program. Neural networks are not good at that level of precision compared to other methods like symbolic AI and more classical techniques are much better at that, and that's where a lot of the verification and logic-based methods were used. But there's like a gap between the type of generalization that neural networks do and what you're trying to do when you generate a program. And I don't know if that's going to be feasible to palliate that gap. I would expect you might use neural network as a first step to get globally the program right, and then you may need to use something else that's not a neural network as a second step to get it exactly right.
Okay. Hello?
Hi, I'm Danny Dick from Oregon State. Thank you for a very informative talk on reinforcement learning and what's possible today and what's the future. So I have a question for you. Our community is looking at how can we improve the quality of software systems, right? And we're talking about until we have the day that computer programs are going to generate our computer programs, a lot of the humans will have to write those machine learning codes. So here in the room we have the best minds in the world in the field of software engineering, and what's the help that you need from us, from our community, to help you to improve the internal quality of those machine learning codes?
That's a great question. I don't know yet is the most honest answer I can give you. I don't know yet, and I hope I can stay and we can have that discussion over coffee, because I don't know yet what it is.
Okay.
Yeah.
I would love to have that discussion.
We'll be happy to.
Thank you.
I think the last question.
Hi, great talk, thanks. So my question is more regarding reproducibility. Well, it's not as much tied to your field, but the challenge of being able to reproduce any research in general, because your checklist is quite extensive. It has like several topics, and often we find ourselves in the constraints of the space of the paper, of the article. So it's hard to fit stuff there. And then we start using links that's 2 years later, 1 year later, are already broken. Not to account for the fact that we often want to show videos and sounds, and we're basically still stick to a glorified, digitalized version of a papyrus. Mm-hmm. Have you ever thought of requirements, or have you seen any research on a better format to share knowledge, share information? Because this is not suitable even for ebook readers. It's hard to
share knowledge specifically about reproducibility.
Share the content, share data sets, share codes that could go with the publication. So when you download, have access to everything, you can manipulate charts or whatever.
When we don't have access to everything?
Well, sometimes we don't,
yeah.
Because links expire, we can fit everything, the paper, because of the size constraints, the length constraints,
yeah.
Like the number of pages. So we're in 2019, and we stick to a version of a paper. There's essentially like a paper scanned. So I was thinking that maybe we could share some thoughts of like requirements, or like which would be your needs to to publish your contents in a better way, in a way that we could see videos, for instance, or what would be your needs in terms of sharing information, not only to reproduce, but to enrich the capture of the information from the reader.
Yeah, there's a different, if I understand the question correctly, there's a few different ways to do that, right? I think the reproducibility checklist, in particular, people have started putting their accounts of their answers to the question as an appendix to their paper. And so that is provided as an extra artifact, complementary to what's in the paper. There's also a number of platforms that are starting to come online where people actually, have a repo and do so in a much more structured way than just a GitHub repo that allows you to replay all the experiments, generate the same graphs as in the paper, and basically locks in all the dependencies for all the libraries that you might have used and so on. So there's a few platforms. It's not clear which one is going to emerge as agreed on from the whole community. Different people are pushing different ones. And it's not clear yet what are the characteristics that are most useful for doing that. I think in a lot of projects there's a concern also that you can't share the data, for example. And when you cannot share the data, presumably you can't reproduce exactly what was in the study. And there's a movement to encourage people to include results both from synthetic data as well as the real data set. So that's starting to be more common. And the other issue we face is with the code submission, particularly with researchers in industry. There's definitely a hurdle in terms of being able to share code. Some companies navigate this with much more fluidity than other companies, I think. And so there's some companies, including FAIR, with whom I work, where open sourcing code is very easy, it's done on a regular basis with almost all papers. There's other companies where that's harder, but researchers have been able to submit at least a component of the code. So it's not runnable code, you kind of surgically extract a portion of it, but it's readable code. And in many cases, that's really useful also. Even if you can't run it, you can actually dig in and see exactly what was done. So I think the standard and the best practices are still really evolving surrounding all of this, and we're going to have to keep a close eye in the next few years about how to do that. And I think that's a conversation to be had with the whole community.
Thanks.
Thank you.
Thank you, Joelle, one more time.
Thank you.
We have a small gift for you.
Thank you very much.
Oh, he wants
Oh,
a picture.
picture. With the gift, without the gift. Oh, handing. Thank you.
Thank you very
so
much one more time.
Thank you.